Our project uses the YOLO model to detect food items in refrigerators. In a brief introduction, our model aims to harness the cutting-edge capabilities of the YOLO model to identify and categorize various food items in a refrigerator. The objective of this project is to train advanced models, specifically by fine-tuning the YOLO model to analyze images of food items within refrigerators. This enhanced model will be capable of accurately detecting and identifying each individual food item, thereby facilitating precise inventory management and improving strategies for meal planning and food storage. The YOLO model utilizes a single neural network for real-time detection, predicting bounding boxes and probabilities from full images in one pass. The YOLO model has been continually improved since its original release in 2015. The latest version of the YOLO model, the YOLO V8, makes notable improvements for the model's ability to generalize on new datasets by the removal of anchoring boxes. Here's a diagram of the YOLO V8's architecture. Please take a moment to pause and review the model. Our dataset consisted of 3,148 images of food items within refrigerators. The smallest image was 189 by 189 pixels and the largest 1,297 by 1,297 pixels. Each dataset was annotated with bounding boxes and food labels. There were 30 classes consisting of common items such as beef, bread, butter, and cheese. There were 107 instances of each food class throughout the entire dataset. During the data exploration phase, we first checked for completeness. We made sure that every single image file had a corresponding labels file. Then we checked for category distribution. We made sure that every single class of food items appeared an equal amount of times throughout the dataset. Then we performed a visual examination on each image. We displayed the image with its corresponding bounding box and made sure that the bounding boxes correctly matched the food items that they were labeling. Then, for preparation of the model, we resized the images. There was minimal pre-processing needed due to the earlier steps. For our model, we decided to use the YOLO V8 Nano, which is the smallest YOLO model available. Its small size allows it to be loaded on consumer devices such as small electronics and smartphones, making it ideal for consumer applications such as recognizing food items in a refrigerator. Initially, we trained the model from scratch on the VOC dataset using the hyperparameters of 100 epochs, a batch size of 64, a seed of 42, and images of 640 by 640 pixels. All other hyperparameters were the defaults. Then we performed transfer learning on this model on our dataset with the same default hyperparameters. Our baseline model demonstrated robust performance across all classes. It had high precision and high recall, as well as a high mean average precision on a 50% IOU threshold, and a high mean average precision on a 50 to 95% IOU threshold. Some of the classes showed high degrees of variability, and there was some confusion between various classes, such as chicken and beef. In our final model, we plan to reduce the variability here and improve the overall performance of the model, and reduce the confusion between certain classes. For our improved model, we performed extensive hyperparameter tuning using the YOLO toolkits. We performed 300 iterations of 30 epoch training sessions over 72 hours in order to find the ideal hyperparameters for the dataset. Our model demonstrated excellent performance with training and validation losses decreasing significantly while maintaining a high F1 score of precision and recall above 0.9. The MAPE scores were across various intersection over unit and thresholds, indicated robust object detection capabilities within complex refrigerator environments. Our model showed strong performance across all metrics. There's a slight incline in our validation loss after 50 epochs due to the fact that the hyperparameters were tuned on 30 epochs. We found that this was an acceptable trade-off given the increased consistency and accuracy of the model overall. This is a side-by-side comparison of the normalized confusion matrices for both our baseline and our improved model. On the right, you can see that our improved model shows less confusion between classes such as chicken breasts and beef, as well as potatoes and bread, apples and limes. Here's a comparison of the precision recall trade-off between our baseline model and our improved model. Our improved model shows a better trade-off of precision and recall over all classes and significantly improved performance on many individual classes. This means our model has a low rate of false negatives and a low rate of false positives. This is a comparison of the precision of our model at various confidence levels. Our improved model shows less variability of the model at higher confidence levels for many classes. This means that our model is less likely to make false positives with a high degree of confidence in its classification, which leads to more consistent and less wildly off labels by our model. Our improved model shows improvements in our recall rate at different confidence levels. Specifically, our model shows a better ability to correctly return many true labels with a high degree of confidence. Additionally, as with other curves, our model has much less variability in its recall and at different confidence levels. Here's a comparison of outputs from our baseline model and our improved model. Our baseline model struggled with double boxes. On the left, you can see that it predicts 2 bounding boxes for a milk object. This is fixed in our improved model. On the right, you can see that our baseline model struggled with misclassification. It misclassifies flour as onions and beef as chicken breast. This is also fixed in our improved model. Briefly covering the applications, our model has applications in kitchen management, restaurant and inventory tracking, and dietary assistance. If you need time to read more, please pause. In conclusion, this model aims to identify and categorize various food items in a refrigerator. It successfully fine-tuned the YOLO V8 model, achieving a precision of 0.95 and a recall of 0.96 with a dataset of 3,148 images. This high level of accuracy and reliability in detecting diverse food items demonstrates the model's effectiveness in real-time inventory management for both residential and commercial settings. The enhanced model supports efficient meal planning, significantly reduces food waste, and aids dietary management, promoting sustainable practices in food consumption.